So we're going to look at recommender systems. These are methods used in online retailers, book recommendations, movie recommendation sites, very ubiquitous in our society right now. So recommender systems, many organizations collect some kind of ratings of items from their users. And so we get data of the form, the user ID, the item ID, and the rating. There's often additional data, timestamps for example. Users tend to rate only a tiny fraction of those items being offered by the organization. The goal then is for each user to recommend unrated items a user will likely rate highly after the fact. In other words, once they have them, they'll really like them. Collaborative filtering comes from the fact that recommender systems are based on the idea that users who rate similarly in the past will rate similarly in the future. This is actually the assumption we use for a collaborative filtering approach to recommender systems. User-based means ratings by user similar to a given user can be used to recommend items to that user. Item-based, we recommend unrated items to a user based on similarity to items that the user's already rated. Now we're going to focus only on user-based nearest neighbors. So it starts with ratings data. And this is just user, item, and rating, and just many observations of those. But we tend to put them in a user items rating matrix. Notice that's going to mean a lot of missing information. The users are going to be the rows and the items are the columns. We'll put a coefficient of 0 for any unrated items, but these are not actually ratings. They are simply inserted, so the user item ratings array is actually a matrix. We can do matrix arithmetic. So let's look at an example, the Movie Lens ratings dataset. This is 1 million or so anonymous ratings of about 3,900 movies made by about 6,000 Movie Lens users. There are 3 files, movies, users, and ratings. The goal is to use the ratings, which range from 1 to 5, of movies from a given user to recommend movies not yet seen by that user. Recommendations are based on predicted ratings for movies that a user has not yet seen. So here's what the ratings data looks like. There's a user ID, a movie ID, a rating, and a timestamp. And there's 1 million rows of these. The movies data is the movie ID, the title, and the category. Users is ID, gender, age, occupation, and zip code. Now, we won't use users.dat or the categories, even though it's excellent information. So we recast the data into what's known as a sparse matrix. See, most people rate fewer than 100 movies. And a matrix that is mostly zeros can be defined simply by a list of the location and value of non-zero entries. But if every coefficient, including the zeros, were to be placed into this very large matrix, the resulting dense matrix, as it's called, would be 180 megabytes in size at least, maybe bigger. Data is only rarely stored as dense matrices. In fact, matrix is important conceptually, but not necessarily concretely. So here we have it. This is the ratings matrix. You see a lot of blanks. Those are where we don't have ratings. So these are the non-zero entries, and we only would store the actual ratings in this sparse matrix. Now theoretically, this is a rectangular array, but in practice, we never actually create this rectangle. So should we recommend GoldenEye to user 357? Well, we've got to go back to Polya's method. We need a better question, which means we first need to explore the ratings data. So here's our exploration. Notice that most users rate fewer than 100 of the 3,900 or so movies. Here are the actual ratings. The mean of the actual ratings is 3.53. But the ratings matrix mean, the mean of all the coefficients in the ratings matrix, all those blanks being replaced by zeros, is only about 0.014, because almost all of those coefficients in the ratings matrix are zero. So if we have a kernel, k of xy, we can predict a rating. So if x is a user row that is not rated item I, and we have ratings 1 to k of item I by the k nearest neighbors of x. Remember, nearest means similar, and that means the kernel is approximately 1 for these neighbors. So if we have r hat is the prediction of x's rating of item I, then r hat's defined by this weighted average. That means we just need a good appropriate similarity kernel. So we don't want to use distances or correlations for many reasons. Notice that a row has a huge number of zeros. That means distances between users is incredibly large, the cursive dimensionality. It also means x bar and y bar are close to, but not exactly zero, corrupting any possible correlations. So we use cosine similarity, comparison on a common subspace. So in cosine similarity, if the x1 coefficient is 0, then we ignore movie 1. If the y2 coefficient is 0, then we ignore movie 2. See, we're only going to use movies that both observer X and observer Y have seen in our estimation of similarity. Unrated movies are ignored. So now we have a better question. If user 357 watches GoldenEye, then can we predict the rating user 357 will give to that movie via cosine similarity between nearest neighbors? So here we have our ratings matrix. Our method is going to use cosine nearest neighbors applied to user 357. The green rows are the nearest neighbors. And we'll only be using movies that the neighbors have in common with the given user 357. So this means that the neighbor's mean rating for GoldenEye turns out to be about 3.96. So our interpretation, user 357 is probably going to rate GoldenEye near a 4. May not be their absolute favorite, but they'll enjoy the movie. So let's see how we would do this with code. We're going to use the surprise library. If you're using the Anaconda distribution, this is how you install it. The movie lens data is already built in. Then we build the training set. We could have built a test set, but we're not going to do that here. We're going to have expected 50 neighbors, but no fewer than 5. Now we're going to fit and then make a prediction. There it's fitting using the cosine similarity. And then it predicts that user 357 would rate movie 10, GoldenEye, 3.96. The American President, movie 11, which has an actual rating of 3.5, it predicts 3.82. But how do we know if these are good predictions? Maybe K is too large or too small. We test the model, where a model again is a representation plus an algorithm. So this time we split the data into 2 disjoint subsets, a training set and a test set. Remember, splitting the data into disjoint sets simulates the sampling of 2 different data sets from the original process or system. So now we build an algorithm and train it, fit it to the training set. Predictions are made on the test set, and we measure the root mean square error of predictions versus actual. So our root mean square error is 1.0205. Now we can also do a thing called cross-validation. Cross-validation means we split the entire data set into CV number of subsets called folds, and we use each time one of the folds as the test and the union of the other folds as training. And we get a report that looks something like this. So now let's see how we can use this to find a best value for K. We're going to do a grid search. That means we're going to repeat a CV fold cross-validation for each of 5 possible values of K. So here our CV is 3. We do the grid search. It's not fast. We'll get the best root mean square error across the entire grid search, and that will tell us what the best K is among those Ks we tested, which are 30, 40, 50, 60, and 70. This takes a while. It's not fast. So it actually repeats 15 times. But then we get our results. Turns out K of 40 is best. And the best root mean square error is 1.02. Now, because this can be very slow, you can define it as multiple jobs and distribute to multiple processors if they're available. Let's look at another example, the small town zoo. This is data designed to mimic the movie lens data, but it's going to be very small. About 15,000 ratings, 250 visitors by 150 animals. That's only about 300 kilobytes of data. That's small even for a phone or a watch. However, the small town data is simulated. It's a random number generator, and the data itself has a rather simple topology, so this is a noisy, simple topology. However, the movie lens data is sampled from a complex system, not a random number generator, and that does make a big difference. So here's the actual data, and here it is as the matrix. Most of the coefficients are zeros, and again, we'll take dot products of individual rows, and all those zeros means that only where the exhibits, they've both rated the same exhibits, will the dot product be defined. So here's the actual code. So we start out by reading in the data as a data frame. Now we need to define a reader and tell it what the rating scale is. Here's a data frame with 3 columns. So this is the head and tail of it. And that's what's required if you're going to load from a data frame, is you have to have the first is always the user ID, the second column's the item ID, and the third is the ratings ID. After that, it's pretty much the same as what we've done already. And here's our results. So Adams and Young, Adams, the alpaca, is actually 5, estimated 3.92, and here we had an actual K of 10. So there are also variations on the way we predict ratings. Remember, this is the standard way. But for a given P, you can let the rating prediction be P plus the weighted average of the ratings on the ith items minus P. For example, P could be a mean rating for item I, or it could be the low end of the rating scale. So in summary, recommender systems predict user sentiment, and where you looked primarily at a collaborative approach, which is based on a user item matrix. We predict user rating of an unrated item via nearest neighbors approach. Later, we'll use matrix factorization to do the same thing. But recommenders tend to require massive data sets, and they tend to use cosine or other non-traditional measures of similarity. And later in the course, we'll see all 3 of these again when we look at what are called kernel methods.